Good afternoon. Can you hear me?
Yeah.
Okay. Good afternoon, good morning, and good evening for everyone. I'm Aaram Kim, a postdoc of University of Freeport, and this work is done by the collaboration with Philip Berner from the University of Freeport and the Diagrammatic Correspondence from King's College London. The solution of my talk is strange metal solution in diagrammatic theory for 2D Hubbard model. Lottinger-Ward functional is formally based on the Lysander transform between the external source fields J and interacting Green's function G. As discussed before, we first introduced the external source fields J in a bilinear term to the action like this. And the partition, we can take the log of the partition function to get the free energy functional as a functional of the external source fields J. Then the interacting Green function become a conjugate variable of the external source fields J. Then we can apply the Lysander transform to get the effective 2pi effective action or the Kadanoff-Baum free energy functional like this. Then the Lottinger-Ward functional is the universal part of the Baum-Kadanoff functional or the effective action, defined like this. Since Lottinger-Ward functional is based on the Lysander transform, we need a well-defined Lysander transform, which assumes that smooth convex functional of the free energy functional omega j. And under this assumption, we have a one-to-one mapping from the interacting Green's function to the external source fields J, or equivalently non-interacting Green's function G0 and or the self-energy sigma. However, checking this assumption, the convexity of the functional of the omega, is as difficult as solving the actual problem in most of the quantum many-body system. So in many cases, the convexity of this free energy functional is simply assumed in many cases. But recently, with the help of the numerical quantum many-body technique, there has been some concrete example in which the convexity of the functional is broken. So the Lysander transform for the Lottinger-Ward functional is ill-defined. And in this case, the problem called the multivaluedness of the Lottinger-Ward functional appears. One of the simple example is shown in the figure right here. It is a very simple model composed of a few degrees of freedom, which can be solved analytically. And in this case, the free energy functional has non-convex form with the inflection points shown in here. With this inflection point, the mapping from the interacting Green function G to the non-interacting Green function G0 is not one-to-one, and there is two different G0 values corresponding to the interacting Green function G. This multivaluedness problem was first reported in the 2015 by the paper from the Evgeny Kozik and co-workers. And there is a first unphysical branch of the Lottinger-Ward function, which shown in green line in the strong coupling regime. And after that, there is a simple models which can be analytically solved. Has been introduced to qualitatively understand the situation. And recently, there is also a report that the number of the unphysical branch is actually infinite. And at the branching point, the eigenvalue of the charge vortex actually diverges, which has a physical implication in the system. And there is also interesting suggestion that this kind of the multivaluedness problem is closely related to the fermionic statistics. in case of the multivaluedness of the Lottinger word functional, the self-consistent solution can change its character depending on which branch we are choosing. So we investigate the 0+0 dimensional effective model introduced by the Ricardo Rossi and Felix Beringer. And there are two different branches. One weakly correlated branch redlining here, and one strongly correlated branch shown up here. Suppose the physical solution is in the weakly correlated branch, and we choose the weakly correlated branch in a perturbative way. Then using the Ball series, for example, then the lowest order Ball series give us a nice approximation, and the result is getting more and more accurate as we increase the expansion order of the Ball series. But when the physical solution is in strongly correlated branch, and we still choose the weakly correlated branch using the Ball series, then the self-consistent solution shown in the open black symbols in here end up with the unphysical solution away from the physical one, even if we increase the expansion order up to the infinite. One of our main claims is that the dimensional generalization of this unphysical solution in the Hubbard atom or the actual Hubbard model in 2D shows the non-Fermi liquid behavior in certain parameter region. Also, there is one important observation that when for the unphysical self-consistent solution, there is a singularity of the Ball series is pinned right at the radius of the convergence. Those figures shows the singularity of the Ball series. And as we increase the interaction strength, the singularity approach to the radius of the convergence and pinned right at the radius of the convergence when the interaction strength is larger than the branching point. The strange metal showing the non-Fermi liquid behavior is one of the most intriguing and mysterious phenomena in the condensed matter physics. There is a universal experimental evidence showing the T-Needler resistivity, which is in strong contrast of the T-square behavior expected by the Fermi liquid theory. The 2D Hubbard model is one of the microscopic model with the electron hopping and the local interaction U. And it is widely believed to incorporate the rich physics of high TC superconductors. On the other hand, there is recently highlighted SYK model, which was first introduced as all-tool interacting spin models with a quantity disorder. And it recovers the T-linear scattering rate, and it is analytically solvable for the large N limit. So it is one of the concrete example of the non-Fermi liquid in this model. So in the remaining part, I want to discuss about the question is there any underlying relations between these two seemingly different models with seemingly different ingredients? That's one of the topic I want to discuss in the remaining part of my talk. I want to point out that there exists the diagrammatic correspondence between the SYK model and the Hubbard model. After averaging quantity disorder of the Gaussian form, the cell point equation of the SYK model in large N limit is written like this, which is the conventional second order Ball series self-consistent equation. And in the Hubbard atom, which is the atomic limit of the Hubbard model, it also shows exactly the same form of the self-consistency equation at the second order. So one of the questions is the Hubbard model, is this correspondence between those two models, SYK model and the Hubbard atom, and Hubbard model, reinforce the position of the Hubbard model as a standard model for the high TC superconductors. So our claim is that the care must be taken because the non-Fermi liquid can be the unphysical solution in case of the multivaluedness of the Lorentz-Ward function. We first investigate the high-order diagrammatic expansions of the Hubbard atom, since we want to check our story of the unphysical solution in the 0+0 dimensional model still holds in the Hubbard atom with the spectral properties. To access the high-order diagrammatics, we use the bold diagrammatic Monte Carlo method, which stochastically sample all possible diagrams, all possible skeleton diagrams up to the certain orders. In this case, we use diagrams up to the 6th order. And we find the self-consistent solution satisfying the Dyson equation. As you can see in this picture, as when we decrease the temperature from high temperature to the low temperature, there is a crossover from the high temperature thermal state, which is exact, which is same with the exact solution, to the low temperature non-Fermi liquid metal. You can see that there is a strong deviation from the exact solution in here. And in the physical solution in low temperature of the Hubbard atom is, of course, molten insulator. And this unphysical solution is actually non-Fermi liquid. And you can see at the second order Bose series, you can see the nice agreement between the analytic SYK non-Fermi liquid solution and our second order solution due to the exact diagrammatic correspondence. And interesting point is that in the high orders, when this exact diagrammatic correspondence is broken, the solution still shows a non-Fermi liquid behavior like in the blue dots in here. And this is definitely metal, as you can find at G beta over 2 value in here. And it is definitely away from the exact value of the Hubbard atom at low temperatures. Now we move on to the actual 2D Hubbard model. The non-Fermi liquid solution observed in the Hubbard atom retain its character even in the 2D Hubbard model. As a measure of the crossover, we define the fermionic scaling exponent delta defined like this using the local Green's function. And this delta captures the long time scaling behavior of the local Green's function. The reference value for 3 different phases of delta value corresponds to the 0 for high temperature thermal state and 1/4 for the SYK like non-Fermi liquid and the 1/2 for the Fermi liquid. And as you can see, as we decrease the temperature, there is a 2-step crossover from the high temperature thermal state with the delta equals 0 to the intermediate temperature non-Fermi liquid with a delta equal 1/4. And from the non-Fermi liquid to the low temperature Fermi liquid, and there is such kind of 2-step crossover. And in the intermediate temperature regime, there is a wide plateau near the delta equal 1/4, showing the clear signature of the non-Fermi liquid in the intermediate temperature. In very low density, there is a direct crossover from the thermal state to the Fermi liquid crossover without any signature of the non-Fermi liquid. In the intermediate temperature, we also investigate the singularity, location of the singularity as a function of doping shown in here. As you can find that the singularity is unpinned in the intermediate density or intermediate doping. So while the delta value stays near the 1/4. So it implies that the self-consistent solution. Near the half filling in here is unphysical, and the solution in the intermediate doping is physical solution. This claims that this gives us the physical non-formal liquid in this intermediate doping regime, and it is consistent with the strange metal phenomenology. So, and this is the summary of my talk, and thanks for your attention.
Okay, thanks a lot. So we have time for a couple of questions. There's anybody in the audience who wants to ask a question? So then maybe I can just ask you. So I was a bit maybe I miss the point. So are you saying that at a certain point, when you use the 2D Hubbard model, the solution that you get with a non-Fermi liquid behavior is a non-physical solution, right?
Yes, near the half filling, very near the half filling, the unphysical solution.
Yeah.
The non-Fermi liquid is an unphysical solution, and the near yes, and in the intermediate doping, there is a certain regime we can find the non-Fermi liquid solution with the singularity unpinning. That's the observation we have in the actual 2D Hubbard model.
Okay, and with the SYK model, you don't find this?
In the scheme of the SYK model, there is a non-Fermi liquid all over the doping, yeah, except very low doping. But under the scheme of the SYK model, we cannot check, or we cannot find if it is the physical or non-unphysical, because it is just a second order self-consistent solution. So we cannot check the location of the Bose series, and it is difficult to say it is physical or unphysical in a systematic way. The reason why we can locate the singularity is that we can access the high orders of the Bose series. So, for example, with the ratio test or some kind of approximation or something like that, we can locate the singularity of the Bose series, since we cannot access the high orders of the Bose series.
Okay, so this is your check. Is it the check, yes, that you do to see if your solution is physical or unphysical?
Yes, yes.
Okay.
And one of the interesting points is that in the phase diagram of the cuprate, the strange metal only appears in the intermediate doping regime, not in really close to the half-filled regime. So our observation is consistent with the phenomenology of the strange metal in cuprate.
Okay, thanks. So I saw that Lucia raised the hand. Lucia, maybe you can ask the question, and Francesco.
Yeah, just more to this. So if you look at your unphysical solution, can you see any wrong analytic behavior in the Green's function or stuff like that?
Not really. That's the one of the points we are claiming that we need to access the high orders and check where the singularity is, check where the location of the singularity. For example, when we see the spectral function of the second order Bose series, then it shows completely fine. It shows the all positive definite spectral function density of state or spectral function, and although there is some peaks in the spectral function, there is nothing obviously seems unphysical in the Green's function.
Mm-hmm. And you implicitly, I mean, you talked about this one-to-one relation between G and G0, right?
Yeah.
so implicitly you have this relation that you give a G0 to a G, and so this G0 that corresponds to a G is somewhere you must run out of the domain, right? Because you should have a...
Yes. Yes. So inflection point divide the domain of the functional, right?
Yeah. So this G0, when you are in the wrong domain, it should be unphysical. I mean, you should clearly have wrong properties, shouldn't it?
Yes, that's true. But the tricky point is that the physical solution changes its domain when we cross the branching point.
Of course.
Yeah, but I mean, but both series by construction always choose the weakly correlated domain,
That is
which
true.
is close to the non-interacting Green's function. So if the physical solution cross its domain, cross the boundary of the two different domain, then yeah, we cannot, I mean, both series cannot access the one of those.
I agree on the problem. I wonder, I mean, why don't you just calculate a Baire series?
Yes, I mean, yeah, for Hubbard atom, yeah. So technically, it is much easier. I mean, for Hubbard atom, the second order is exact using the Boole series. But I mean, our focus is about the physical implication of this breakdown of the Luttinger-Ward formalism. Because,
I understand, yeah.
Yeah. So it's not practical. It's not practical purpose to use the Boole series for the Hubbard atom. We want to investigate or the study about.
Yeah, no, I understand this. I was thinking beyond this. I mean, this problem of the Boole series, I think we all agree on it. And the question is then if on the long term we want to continue to use it. Because the problem is that it's not that it's not converging, it converges to the wrong result, right?
Yes, it converges to the wrong result.
And that is very dangerous.
Yes, that's true. And that's the reason why we need to check the location of the singularity. Yes, that's true. So yeah, I mean, I agree that it is quite tricky. I mean, tricky to use, and we need to be very cautious about convergence to the unphysical solution. But I mean, if we are free from, I mean, if we have a self-contained way to check if it is physical or unphysical by location of the singularity, then Boole series has some benefits, like we don't need the number of the diagram topologies decrease compared to the Baire series, since we have the two particle irreducibility in the diagrammatics. So there could be some parameter regime where the Boole series is very efficient, but I think that's my answer. Yeah.
So maybe we can come back to this in the general discussion, because there are three questions left. I will leave them for the end because it's a hot topic.
Okay. Yeah.
So maybe we pass to the next talk and then we come back on this issue.
Okay.